be 0 if I wasn't paying attention to the small variation dy. But they are not 0 because this difference gives me what? Exactly, tell me exactly. So for example, if I consider the first term and the third term, what do I get by subtracting those two? So I have the function f sub x.
F of x y minus f of x y plus delta y?
F of x evaluated y minus at y plus dy. But what is that?
You get it's the partial of f(x) with respect to y.
Exactly, yeah. So yeah, so and then yeah, exactly, yeah. So all right, so f at y plus dy minus at y gives me the partial derivative times dy, but because I have a negative, I get a negative. So I get minus the derivative of fx at xy with respect to y. I had a dx already, and now I have an extra dy because I took the derivative with respect to y, okay? And again, maybe too fast, but something for you to, okay? And then this one over here is plus derivative of fy at xy. The shift now is in x, so this derivative is with respect to x. I already had a dy there, and because I'm taking the derivative with respect to x, I get a dx. Okay, and we get this thing here. Okay? So it turns out that, look at this here, the curl that we proved last class, dfy with respect to x minus dfx with respect to y. That's exactly what I got here, only times dx dy. So I proved already, not the whole thing, but I just proved that Stokes' theorem is correct in this little patch. Okay? And maybe it's not 100% clear to everybody, I understand that. But doesn't really matter. All the ingredients there, you take a picture, you have the movie there, you can reconstruct the argument, you finish it up. Okay? But the bottom line, what I just did is I convinced you, hopefully, that Stokes' theorem is true for that small patch, where I take C to be the square and S to be the inside of that square. Okay? Once that's done, because I just proved explicitly that the two expressions are exactly the same, then it is just 1 second to prove Stokes' theorem, because the argument, and you have to think about it, is the following. The surface integral is nothing but a sum of patches according to Riemann sum. No problem. So this term on the is immediate and very simple. But what about this one? Well, this one comes about because of the following trick that is very similar to the divergence theorem. So when I did this in this patch, I didn't worry about the neighbors. But let's suppose now that I look at what happens in the neighboring patches. Okay, and so for example, if I look to the right, I'm going to have something similar. So I walked this one this way, to the right, up, to the left, down. That's what we did. Okay, I'm going to respect that orientation, and I'm going to walk this new guy, the color one, same way. So I'm going to walk to the right, up, to the left, down. And so look at those two things. They cancel out because the field is exactly the same on that line, but here I'm walking it up, walking it down, and when you do that, the DLs, vectors, are exactly the opposite, so there's going to be a cancellation. So when I do the line integral on the left patch, I get something, and when I do it on the right, I get something else, but then eventually I don't need that. And if you keep doing that argument, you are going to get rid of all the little patches until you reach the boundary where you cannot eliminate Proust-Stokes theorem, okay? So I'm going to stop here, and I think because you have all the information, you can actually reconstruct. So I'm going to post that in Canvas for you to finish up and give me the full solution.
When you were adding the perimeter of the square, so and choosing the different sides of the square, so did it make a difference which point you used, whether you use like XY or just XY or?
Yeah, you asked me that again last class, I think. I mean, if somebody asked me at least. So if I bring that back, your question is, so I started from XY, and no problem that this is X plus D, that's fine. But what about this problem here, this point here? That's what you're asking me, because this one over here would be X plus dx, comma, Y plus dy. Yes? Now, I have, within my approximation, linear in the x and the y, I can, first of all, I can always do this. Given a field defined in this region, I can evaluate it anywhere in that segment. I choose this one. When I have it here, I evaluate it here. When I have it here, I evaluate it here. And when I have it here. So I never need that point. But again, it's the same answer that I gave last class, okay? And that's something you need to spend 10 minutes and convince yourself. But if you use that point, it's going to introduce only terms that are proportional to the x squared and dy squared or dx dy. Okay, and so when you do this type of analysis, assuming that dx and dy are small, you neglect everything that is a product. Okay, so that's the reason for that. One is that I can do it, and second, why is that I'm not making any mistakes by doing that. Okay, so but try to spend a few minutes on that, and if you still don't see it, then you can come and ask me. Okay. Okay. So now we have those two very important results that we are going to return later to. Okay. All right. So now let's. Any questions about this? Okay.
I get the dx dy for that.
So sorry.
The dx dy, where is it coming from?
Well, so either one of them come from the lengths dl. So for example, in the first term, dx comes because this dx.
How do you get both dx and dy?
Oh, okay. Yeah, that's the second thing. So if you look at this term, at these two terms together, so let's look at these two, which are nicer. So this is the function is f sub y, and the first term is evaluated at x plus dx, and the second is evaluated at x. So if I subtract, it would be almost the derivative. To get the derivative with respect to x, I need to divide by dx, but it's not there, so I need to multiply times dx. So that's why. But the definition of the derivative requires to divide by a small dx. Okay? Okay, so all right, so from now on, all this stuff I'm going to use freely. Okay, and so okay, so now let's get started with the physics now. And all right, so we're going to spend a little bit of time on electrostatics, and that's eventually at the end of the course we are going to get to the full electromagnetism, meaning the combination of electricity and magnetism, and we are going to study the Maxwell's equations and some very important solutions of Maxwell's equations, and also apply to some fun problems in optics. Okay, because optics at the end of the day is an application of electromagnetism. Okay, so we have a relatively short course, and so the way we are going to do it is we are going to spend a good amount of time in electricity, and a little bit of time in magnetism, only what is necessary to be able to blend electricity and magnetism together, okay? So magnetism we are not going to do by itself a lot, but the good news is that except some special materials that are important, a lot of the mathematical techniques that we are going to learn to solve problems in electricity are also good in magnetism. Okay, and there are a lot of parallels. All of us, of course, are familiar with magnets because you can just buy a very strong magnet today and play with it. But we are not that much familiar with objects that are called electrets. But they exist and they are used in technology, and they are just basically electric magnets. Okay? Once we understand the mathematics, once we understand that a magnet is, unless you look very close, but basically a dipole, of some sort. In the case of an electric case, it's a little bit simpler to describe in terms of a case of an electric dipole, and we are going to.
An electromagnet?
Oh, so a magnet, a natural magnet. Is built up macroscopically because of some microscopic domains, okay, because of the spin. It comes from properties of the atom. In the case of a ferromagnet, no, you can actually you can produce the same effect in the space around it simply by circulating a current in a coil. But the effect is the same. Is that your question? Yeah. But what I'm saying here, I want to emphasize that there are a lot of techniques to solve problems in electricity that are very similar to magnetism. Okay, and while there are other things that we are not going to do, okay, because it's a one semester course, still I just want to let you know that a lot of the things that you learn for electricity are good for magnetism. And so when we get to magnetism, we are just going to use it to be able to blend the two things together and start studying the full electromagnetic equations. Okay, so to get started actually it's going to be a lot of fun to get practice with all these techniques to solve problems. We are going to start, eventually we are going to forget at some points that we are doing physics, but we come back to it often. But we need to start, as opposed to a class in mathematics, we need to start from some experiment. And as you know, if we are going to do electricity, the core experiment in electricity is Coulomb's law. Okay? So what we are going to do is spend the next few minutes, maybe the next half of the class, in things that you should already know. And okay, so maybe when you saw them the first time in freshman physics, it wasn't that clear, okay? And that's absolutely normal. I think probably if you look at quantum mechanics, if you look at classical mechanics, if you look at thermodynamics or statistical physics, I think that electromagnetic, every course is special in one way, but electromagnetism is special in that, at least in my opinion, from what I've seen, is that you really have to go over the same material a few times to eventually understand it a little bit better. Okay, so you learn some of the concepts in freshman physics. Here we go over some of the concepts a little bit deeper. And if you go to graduate school, you go to physics or some engineering field, you are going to take also a course in electromagnetism, most likely, unless you do some engineer that doesn't require that. But the point is that you are going to go over the same concepts again and going to get a very different understanding the third time around, okay? And the fact of the matter is that if you, for some reason, work in that field, turns out that you are going to keep learning, okay? And so the electromagnetism is special in that way, okay? So for that reason, I think it's very much worth reviewing problems and try to to emphasize different aspects. So at the very beginning then, we're just going to go over things that we already learned, but very quickly we are going to start learning new techniques that are new to you. Okay, we are going to look at eventually it will be amazing that we started from Coulomb's law when we get to some solutions. I'm going to try to emphasize that. Okay, so
Is that one still blinking blue?
yeah. Okay, so like in general, with problem solving, and the more complicated they get, the more important is what I'm going to tell you, is that notation is extremely important. And I'm going to emphasize that. Okay, so two things, notation. So if you understand what you are doing, really you should be very, very careful in your writing. Because if you write very carefully, then the problems will just solve by themselves. Okay, sometimes. And the other thing is, try to exploit, I like to say this all the time, try to exploit as much as you can the dimension analysis, meaning in practice, try to put as much as possible all the expressions in forms that don't have units. Okay, and so what am I talking about? So I will give you some examples immediately to try to get the important physics out and move the math a little bit to the side sometimes when maybe we don't need to pay too much attention to that. So, but I will give you examples, okay? So then let's get started with Coulomb's law, and everybody knows about it, but immediately I'm going to introduce notation to make our life much simpler, okay? So everybody knows, some from high school even, that Coulomb's law is just the force between two charged objects, and it has a magnitude of the product of the charges divided by the distance squared, and there's a constant factor up front which you can justify that you need to fix units. Okay, so fine, that's one first answer, but clearly the force is a vector. Okay, so what about vector? So now we keep talking and we say, well, if I look at the force on one